Hi, back from intermission, gone to refuel, and on to soil formation. So we're going to talk about the different mechanical and chemical processes that cause soil formation, but at the very basic form, you have rock, you have rock that slowly disintegrates over time. So usually most of the processes that are causing that are on the surface. So you tend to see more soil formation starting at the top and working its way down as those processes penetrate through that rock. And we call those different layers horizons. So we'll get to that eventually. We'll talk about horizons in a PowerPoint. So one of the first things we need to talk about is weathering. So you can have physical weathering, and that's basically just the disintegration of rock into sand, silt, and then clay, turning big rocks into smaller rocks, right? Hulk smash. We are not changing the chemical structure at all, just making bigger pieces smaller. Whereas with chemical weathering, it's an actual decomposition. So the chemical structure of the rock is changed. So classic example of this is rust, right? Oxidization. We're changing that iron mineral into an iron oxide mineral. You also see this with minerals that can dissolve. So a lot of caves have a lot of chemical decomposition of minerals in them. And then I can't talk about physical and chemical without also talking about biogeochemical. Later on in the year, I do a whole lab lecture on the biogeochemical processes. But basically, this is when we start talking about how the biology that is growing in those soils can then weather the soils chemically. So I want to talk about some of the chemical reactions that happen in soils. In a non-COVID year, I would have these three things: hydrolysis, carbonation, and oxidation redox reactions. I'd have examples and get you guys to actually do some of this in the lab. I'm going to try and figure out some take-home experiments where you can do some of these. That you guys can definitely do carbonation at home, and see if I can figure out some other ones that we can do and actually see these chemical reactions taking place. On the side here, I have oxidized basaltic rock, so it's gone from gray to red, and we'll talk about what oxidation is. And then this is dissolved limestone rocks, where the chemicals in the water have dissolved it, so dissolution. Hydrolysis is slightly complicated chemistry, but basically the presence of water chemically breaks down the rock by replacing the mineral itself. So you're like you're breaking hydro, water, lysis, break. You're breaking with water. So in this classic example, we have potassium feldspar plus water, and the water sort of breaks apart the feldspar in such a way that you create a clay. So feldspar is quite a hard mineral, whereas kaolite clay is super soft. So it breaks apart, it chemically changes that feldspar into kaolinite, and then the kaolinite easily gets washed away physically or rubbed away physically. So that really can chemically changing the structure, which then allows it to be physically weathered a lot simpler. Dissolution and carbonation kind of go together. This is a picture of bricks that are made out of limestone that have been sort of dissolved from acid rain. So dissolution is simply some minerals dissolve in water. You've seen this when you've mixed salt into water. And this is a process that is reversible, because once you remove the water, the salt is still there. So that's why we have salt flats, like in Utah or Bolivia. Those are old salt lakes where the salt was dissolved, and then once the water's gone, the salt remains. So this is basically how caves form, is the water dissolves the mineral from one place, transports it, and then it forms in another place. Carbonation is when you add carbon to the water. So carbon dioxide is present in the atmosphere everywhere. All the living things are breathing it out, even if we didn't have all of our cars and furnaces and everything pumping out extra carbon dioxide. We'd still have it in the atmosphere. So carbon dioxide easily reacts with water to make carbonic acid. We learned this in first year environmental science and probably in first year biology as well. And carbonic acid is going to decay minerals faster. So things that might not have dissolved in just plain water, they will dissolve in that carbonic acid. And a classic example of this is limestone calcium carbonate. It's totally fine if you have a slightly alkaline water. Calcium carbonate is great. But as soon as you have a slightly acidic solution, like carbonic acid, it starts to dissolve. And that's carbonation. And that's what's happening to these limestone bricks. And it's one of the reasons why climate change and carbon levels in the atmosphere are problematic, because we're changing the carbon content of the oceans and lakes, and the slightly acidic water is going to start breaking down the shells of all these critters and any limestone rocks. So it really speeds up processes, and this is one of the reasons we get sinkholes, because if we have acidic rainwater flowing through these underground water systems, it speeds up that natural dissolution process, and then you get a sinkhole. Then we come to our redox reactions, oxidization and reduction. So really simply, oxidization is when minerals lose an electron, right? Do you remember Leo the lion says grr? Lose an electron. And reduction is gain an electron. Reduction gains, oxidation loses. So basically, oxygen is added. Oxidization, iron, slow down, Oriana. So say we have iron. Iron is usually a steel gray. When there's an oxidization happen, iron loses an electron to oxygen. That's why it's oxidizing, and it turns an orange color, and that's what rust is, oxidized iron, iron oxide, which is what we're seeing here in these patches. So we've had water flowing through this system, which has introduced oxygen to this rock and allowed the iron particles in that rock, in that soil, to become oxidized. Reduction is the other way around. So again, let's go back to that iron. Iron is that steel gray. When iron gains electrons, it then becomes a sort of whiter, steely blue color. So it ends up being in anaerobic environments, which are, oddly enough, often saturated with water. So there is oxygen in water, but when that water is left alone, there's no way for the iron to access the water, to the oxygen. So if you have totally saturated with water and no water movement, then you'll get reduced soil. And if there's a lot of iron in that soil, it'll actually become like a greeny blue color. And I've seen it a few times in my life. It's super cool when you find these reduced iron-rich soils, usually at the bottom of ponds and bogs. But typically what you find is movement of water, and if the water table shifts where you have saturated, not saturated, saturated, not saturated, then you get this reduction, oxidization happening back and forth, and that's where you get this as modeling, where you get this glade gray soil and these red oxidized soils. And so this helps us know where the water table is in our soil sample. If we're cutting down into the soil, we can figure out how high the water table is by seeing those. The classic weathering word, clorped. I don't know who makes these things up. Climate, organisms, relief, parent material, and time. And then sometimes you'll see when people aren't using the word chlort to remember this list of 5 things, people will use biota instead of organism, and they'll use topography instead of relief. Because relief is not a word we use very much, but someone was trying to make it into a sayable word, so they used relief instead of topography. Climate has so many things that affect the weathering and eroding of soil. Precipitation is a big one because wet places have more chemical reactions than dry places, because a lot of chemical reactions are sped along with the process of water. So chemical weathering happens more often where there is wetness. Water also can cause physical weathering because it can freeze into ice. So where you have a lot of water and temperature fluctuations, you can have physical weathering due to that water taking up a certain amount of space, and then as it freezes, the ice takes up more space and it can actually break rocks. And in this picture, you can see the water content in the soil has frozen and pushed the soil particles around. So this is something you see a lot in late fall and early spring, especially when we've had a wet fall. So it really depends on how permeable the parent material is, because a permeable rock will allow water to flow inside of it and then freeze and break it, whereas an impermeable rock, the water is just going to flow over top, and it might affect the surface of that rock, but it's not going to get inside of it. But then if other things get inside and crack that rock and give holes that allow the water to get in, then you can have more physical weathering. The other thing about climate is temperature. So despite what I just said about cold causing physical weathering, the heat is more likely to cause chemical weathering. So in hot places, you're more likely to have more chemical reactions. You're also more likely to have more biota in hot places. So if there's a warm temperature, you're going to have more biological weathering, physical and chemical, from the plants. And then any extreme changes, just like we were talking about the changes in temperature of where we have water causing those the crystals to grow, that happens where we get these freeze-thaw cycles, can be very damaging on the soils. So we have something in North Bay and pretty much anywhere on the Shield where there is cold weather, a frost heave, where the soil has these large rocks sort of underneath. So you have the surface soil on top, and deep underneath there's rocks and boulders underneath what we're walking on. And if the water gets down deep enough, you'll actually have that crystallization push up some of those rocks, and it's called frost heave. And you'll see it in the roadways sometimes where a new bump will form under the road. And it's why, I don't know if you guys have ever noticed, but they'll say like half load restrictions, half load in effect. Those are to stop like big dump trucks from driving over those frost heaves, because in a good situation, the frost, as the water particles freeze and take up more space, that'll push the rock up, but then when they thaw again, the rock will settle back down. But if you drive heavy loads over top of it, then it breaks those crystals and the rock heaves in weird ways, and that's how you get a lot of potholes. Yeah, it's kind of neat too, because in some of the roadways in North Bay used to be corduroy roads. So corduroy road is when they took logs and laid them down, and then they just paved the asphalt over top of those corduroy roads. So the frost heave will sometimes bring logs up out of the ground, which is kind of a neat little historical thing, because those logs are probably 100 years old. The last one is hot days and cold nights can cause cracks. So that's what happened to this rock, is the really, really hot sun heated up that rock, and then when it cooled down, the outside cooled faster than the inside of the rock, and it broke. So the cooling particles getting closer together what's the opposite of expand? Shrunk fast enough that it cracked. And you can do this if you've ever had a campfire with rocks around the edge. If you get a really, really hot campfire and then pour cold water on one of those rocks, you can make them crack from this outside cooling down faster than the inside of the rock. So continuing on with our calorped, O for organisms. I want to talk about plants first. They probably cause a much greater effect on soil formation than animals because of all of the root systems. So roots can physically break down that rock or regolith and turn it into smaller pieces. And you see this with like lichen and mosses growing on rock faces. They're slowly creating soil, slowly breaking apart that rock. And you'll see it bigger with trees, growing through their roots, growing across the rock, any crevice they can find, slowly breaking into that rock. But plants also can chemically erode those rocks because they're uptaking nutrients from those minerals and depositing other chemicals, and it can slowly chemically break down rocks. And then the other way plants affect soil formation is they literally become soil, right? Grasslands are creating soil from the roots up. They're shedding roots, the roots are rotting into soil. And forests are creating soil from the top down. They're dropping all their leaves, and those leaves are rotting into soil. So in terms of soil formation, they break down mineral soils, but they create organic soils. I want to talk a little bit about biogeochemical processes. I'll talk more in another lecture, but this is what I was talking about in terms of plants chemically affecting the soil, because this is biogeochemical weathering, because it's chemical, but it's happening through the plants. So trees are absorbing nutrients out of the soil, and then the leaf contains those nutrients, and then it drops those leaves, and certain nutrients go back into the soil. So it depends on what's in the soil and what's outside of the soil. So for example, conifers grow in acidic soil, and they produce acidic needles, and they don't need as much calcium and magnesium and potassium. So you get these very acidic, shallow soils in conifer forests. Whereas deciduous trees, they need more calcium, magnesium, and potassium to grow, so they tend to grow and pull more of that out of the soil, and therefore create soils that have these higher pHs with calcium, magnesium, and potassium in them, which is kind of interesting. And then we have animals. So I've got a picture at the bottom here. These are swallow nests. So birds have tunneled into the side of a cliff face. Whether that's sand or sandstone, I don't know. And this is a bee. A lot of different bees will tunnel into soils and dig burrows. Not all bees make hives, which is kind of interesting to know. So we talked a little bit about this when we talked about the biota. We talked about how some animals are digging down into the soil and other animals are breaking apart the soil. So shredders and decomposers are the ones that are eating the plant material and breaking it up and helping speed up organic soil creation. And then our burrowers, we call them mixers, like gophers and worms and ants and moles and salamanders. They're all burrowing and digging into those mineral soils, so they're mixing the minerals around, but they're also giving access to water to do all of the chemical and physical changes that water can do. They're giving access to plants to do all the chemical and physical changes that plants can do. And then when we talk about how animals affect soil, we can't forget about people, because we do a lot of stuff. So this is actually a spot where I would stop and I'd let you guys talk for a minute and tell me all of the crazy things that people do to affect soils. But because we're online, I'm just going to go to the next slide. So humans do a lot of soil destruction as well as a little bit of soil creation. So like one of the things when we talk about soil destruction, in my second year class, I talked about prairies and farmland and how that's a huge destruction of habitat that we don't typically think of habitat destruction because they're these beautiful idyllic lands, but farmland is often at the loss of wild habitat. And depending on how the farmer is farming, they could be really destroying the soils that they're using. So a lot of modern industrial farming techniques are not good for soil, and they're actually depleting soils. And we'll talk about that again later in the year. We have deforestation, which destroys soils, and acid rain depletes soils, and obviously mining, urbanization just totally like paves right over soils. None of these things are good. And then sometimes we create soils. So a lot of golf courses are helping with soil creation. We're adding soils to places. We're manipulating soils in ways that we wouldn't be like clear on, like we'll add sand and organic matter to places. Golf courses are weird. I'm not pro golf course on the environmental science side of things. But we also create like gardens. And this is something, a new fad in buildings. We're adding rooftop gardens. MEC in downtown Toronto has a beautiful garden on the top of their building. And this is the creation of soil. And we have compost and we create soil. And landfills technically are soil creation in a weird way. Where, yeah, we don't want to build our houses on top of a landfill, so then we leave it alone and allow nature to take over again. Continuing on in our CLORT, we have relief or topography. I've got 3 parts to this, is slope, aspect, and the position of the landscape. So the slope is basically how steep your slope is. So if you have a really, really steep slope, you're going to have more erosion due to gravity, like physical erosion. You're going to have less water retention because the water's just flowing down, and fewer plants. So steep slope leads to more soil destruction because the plant roots would be able to hold that soil together, and having those exposed surfaces gives more opportunity for water erosion and physical erosion. So you can see here, this is on this picture, where's my pen? On this picture, you can see this is a really completely steep slope. That's about as steep as it gets in terms of slope. And then this scree hill is loose material coming down from up there. Very few plants, a lot of erosion happening. The opposite of a steep slope is when you have a depression, and then a depression will hold water in it. So then you get different kinds of weathering in a depression, but often you'll get soil formation rather than soil loss. Another part of that relief is aspect. So this is basically what direction that slope is facing. So a north-facing slope is going to be colder and wetter. Snow will stay longer on a north-facing slope. There'll be more dew and frost on north-facing slopes. South-facing slopes are going to be warm and dry. So depending on what kind of vegetation, you might have less vegetation growing on a south slope because it's drier, or you might have more vegetation growing on a south slope because it's sunnier. Just depends on where in the world you are. And then like there's the basic landscape position. I've got sparrows in my backyard. Right, so the top of a hill is going to see different weathering situations than the bottom of a hill. So just that basic position in the landscape helps form the soil formation, the weathering that you would see happen. The P of CLORT is parent material. So whether you have an organic parent material, like the top of this podzol soil is organic, or if you have an inorganic material, like the red mineral sand of this is what we call a ferrohumic podzol. This is very common in the North Bay area. We will see more of these throughout the year. But when we talk about inorganic weathering of soil. So organic weathering, typically made of plant materials, typically forms in wet environments like bogs. But inorganic, you can have residual and transported. So this is residual formation. This sand here is being created in that location. And you're getting these stratified color bands as the weathering, the acid water from the soil is going down and leaching through and then oxidizing the iron down here. That kind of weathering is all happening in situ. The rocks underneath are being broken down and it's all happening in situ. But a lot of inorganic weathering is because soil is transported. So that's a whole another set of slides I'm going to go through. So one way that soils can be weathered and transported is lacustrine, so like lakes. And you usually get these really fine layers at the bottom of a lake. And we are talking about slate and shale being created from fine clay particles being deposited in a lake. So that's a kind of weathering. Alluvial or fluvial is water movement. And soils will be weathered and eroded by the water moving past those mineral soils and then deposited elsewhere. So this is a picture of how an alluvial fan works, and this is an actual alluvial fan. So the river picked up that water and then deposited it where the energy flow stopped. So the river's moving fast through this mountain chain, and then it gets to the end and it just loses all its energy and deposits all that material that it's been carrying. You also see this in like deltas, in when a river hits an ocean. In marine situations, so lacustrine is lakes, marine is ocean, and you get these very, very, very fine particles because the heavier particles will land closer to shore. It's only the super fine particles that end up at the bottom of the middle of the ocean. And often they're organic. So like this is a chalk cliff. That chalk is completely made up of tiny little organisms and their shells, because that's the only thing that's out there in the middle of the ocean are these microscopic organisms. So marine deposits, again, typically in very fine particles and fine layers. Colluvial is like similar to alluvial, but without the water. So here we have angular, anything that traveled in water tends to be smooth because of the way that water moves rocks and sand around and wears it down. But large angular pieces in colluvial. So this is kind of a classic one where gravity, weathering of whether by water or chemicals or heat or sun has broken apart this and it's fallen down this hill. And this is colluvial transportation. These piles, probably like scree hills like we saw on the other one, that slow creep down the rock face. Tills and moraines, these are, this one you can see is round, so this is transported by water. This one's layers. These are from either glacial till or river till. So as the glaciers transported, they were angularly picking up rocks and pushing them. So when you get to the moraine at the end of a glacier, it tends to be angular material with some rounded. But then underneath that glacier were rivers flowing out into like at the end you'd have like a glacial lake. Those rivers left glacial till in a different form, and those eskers typically have rounded material in them. So that's another form of mineral transportation. And then the last is aeolian, so that's wind. And these typically are very fine particles, so you get layers of soil, but sand dunes are also aeolian particles being moved across the area. And then those fine sand particles that the wind is moving will also erode, like physically weather other sandstone in the area. So you get these beautiful round, beautiful eroded surfaces like this like this drawing here, where some sand has hit other sand and eroded it. The fine desert sand, when I lived in England, if we had an interesting weather pattern, we'd actually get red dust from the Sahara landing and coating things. This happened not regularly, but when I was there, it happened where like we got up in the morning and there was like a red dust over everything. And that's Aeolian transportation. Very fine particles getting lifted up and moved long distances sometimes. So chlorpt ends with time. And basically, a lot of these processes take time. So when we talk about time, we're not necessarily talking about the age of the soil, but the degree of weathering. An older soil typically will have more time to have become weathered. But sometimes that happens quite fast, sometimes it happens slowly. But this is that picture from the beginning where we have the bedrock that then the rain physically and chemically starts breaking it up, allows plants to deposit organic matter, and you start seeing a more complex soil where you have organic matter at top, and then it's no longer rock, you actually have mineral soil. And then the longer again it takes and you start to see horizons of different kinds of mineral soil. Plant roots are getting deeper, there is less rock underneath. That just takes time, right? So when you have a young soil to a mature soil, it can take hundreds of thousands of years sometimes to break down all of those rocks. How long ago were the glaciers? They're still all over Northern Ontario, bare bedrock. It's too long it hasn't been long enough for the soil to be created. So I'm going to end this PowerPoint with 4 processes of soil formation. And again, here is our ferrohumic podzol. And these are the soil horizons, these layers, and we'll talk more about that, I think, in the next PowerPoint I go through. So the first one is transformations. So down here we have a mineral soil that has iron in it. And the water that is coming from the top coming down is oxidizing that iron, so that as you look up, the soil is being transformed from this pale yellowish color to this vibrant dark orange red. And that's because there's more oxidation here than there is down here. So this is a transformation of the soil. It's being chemically changed, but it might also be physically changed. This rock is probably more sandy. This is probably getting broken down and has a little bit more silt in it. So it's physically different. Translocation are movement of material within the soil. So in this case, in this ferrohumic podzol, you have acidic topsoil from a variety of reasons we'll talk about. But that acidic topsoil is, if you touch it too long, it goes weird. The water will leach down, and it will actually, the water will take the minerals out of this AE layer, and it will transport them down. And that's what's causing this to be white, is the leaching of minerals, and this to be orange is the bringing those nutrients down into this. This is a translocation, that leaching. This can happen vertically, but it can also happen laterally, depending on the flow of water or root systems or whatever in your soil. We can also have addition. So in this case, we have new leaf litter being added to this soil at the top, which is going to grow that organic layer over time. You can have other kinds of additions coming in. Water can seep down and bring in dissolved minerals and add additions in that sense as well. And then you also have losses. So in this kind of soil, a very common loss are burrowers. They will dig down and remove soil out of that material. You can also have loss through chemical reactions. So like we were talking before with the leaching, this layer is going to lose chemicals as they get leached down. And this area is going to gain chemicals. So you have physical as well as chemical additions and losses. I think that might be it. So that's it for our soil formation. Next time I see you guys, we're going to start talking about soil horizons. So that profile that I just showed you of that ferrohumic podzol is showing you different horizons. So we'll start in explaining more about that in preparation of starting to actually dig some soil pits, maybe. All right, I'll see you guys soon.